Hello and welcome to topic 8.6, Gauss's law, daily video number 1. In this video, we will define Gauss's law for electrostatics to lay the groundwork for application. My name is Eastman Landry, and I teach at the Kinder High School for the Performing and Visual Arts in Houston, Texas. Here's Gauss's law in all of its glory. Essentially, it's talking about how electric flux through a Gaussian surface depends on the charge enclosed by that surface. So here I have the definition of flux that we have here, that symbol from before, which is charge enclosed over epsilon naught in this particular case. But if we relate it to the other side, this thing boxed here is our Gauss's law. We're going to define what a Gaussian surface is here in these next couple of slides. But the main thing to take away is what all these different terms are referring to that we've talked about previously for electrostatics. So let's hop to it for our application and how we use Gauss's law and exactly what all these different sides and terms mean and how we apply them to situations. So a Gaussian surface is any three-dimensional closed surface. That's kind of a key idea there. And we note that because we have this little circle thing around the integral sign. So that's what that means. It's a closed surface integral. The loop that's there means it's closed. And here's the quick note, just very briefly. If you see other textbooks, other websites mentioning it like this, that is definitely another way to write a closed surface integral. But on the AP equation sheet, we're going to write it just like this, and that is absolutely a-okay. The key thing is that that loop is what makes it. So if you wrote this is actually not Gauss's law because it's missing the little loop thing. You have to have the loop there to define that it's a closed surface integral. So just a brief note what that's referring to. So we have the left side and the right side of Gauss's law. On the left side, we call it the easy side. Why is it easy? Because the situations that we pick are going to be highly symmetric situations that cause this E.dA term to be very straightforward. I know it looks intimidating because it has this closed surface integral that's, some early vector calc stuff, but for what we're doing for AP Physics C, the symmetry makes this very simple. We're going to watch on for that one. So hooray for the easy side. Unfortunately, or fortunately, depending what you're looking for, we have the right side, which we call the tricky side. This Q enclosure epsilon naught might seem deceptively simple, but if we have a varying charge density as a function of radius, we're going to have to use calculus to integrate to solve for that total charge enclosed. Ultimately, we're going to explore this in videos 2 through 4 for this unit, but today we're going to focus on this video. We're going to focus on our symmetry. So here's some common symmetries that happen for this particular course. They're either going to be spherically, cylindrically, or planarly symmetric. What does that mean? Well, they look like this. You have a sphere or a point charge that has charge on it. We're going to use that symmetry. If we have cylinders or lines of charge, we're going to use that symmetry. And if we have planes or uniform shapes, we're going to use that symmetry with particular shapes that go with each one. If you're like, well, how can I learn to solve each of those? This is the breakdown for the next 3 videos. In video 2, we're going to deal with plates, video 3 with cylinders, and video 4, the very last one, we're going to deal with our spheres and point charges in this topic. So for today, we're going to just kind of take a general summary of how we approach each of these common symmetries. So let's take a look at what these Gaussian surfaces are. I like to call them the big 3 because they're the main ones that we're going to use. The main thing we're looking for is to create a surface that makes it so the E field is perpendicular or parallel, which simplifies our surface integral. Why? As a quick review of the dot product, if we do E dot A, for example, if we do cosine of 90 degrees, that's going to cancel out. If the vectors are perpendicular, it'll cancel out to 0, versus if they're parallel pointing the same way, that'll make it be 1. So that simplifies it, and that's what we're looking for. So what do these surfaces look like? Well, we have the Gaussian sphere, you have the Gaussian cylinder, and the Gaussian pillbox. You might say, well, wait, the Gaussian cylinder and the Gaussian pillbox look almost the same. Sure, but the key idea behind the pillbox is traditionally it was a defensive position that would be built, and people would be standing on, I guess, the end caps, and it'd be kind of a vertical cylinder. And that's why we tend to use this one as a reference, because we care more about the end caps of our Gaussian pillbox, where we care about the sides of our Gaussian cylinder. Let's see what this looks like. So we have a Gaussian sphere around a positive point charge. It would look something like that. Our E field lines would be going outward through this Gaussian surface, which is just an imaginary surface that exists there. And at every single point, the electric field would be perpendicular to the surface. Again, perpendicular to the surface means that the angle between the area vector and the E field vector would actually be 0. So this is maximizing the flux. Looking at the Gaussian cylinder, this one happens to be around a negative line of charge. These E field lines would be going in. And if you notice, the cylinder walls are what have flux, but the end caps do not, because the flux or the E field is parallel to that surface. Lastly, we have the Gaussian pillbox, and this is going to be of a positive sheet of charge. We're going to have these E field lines going up and back down again. Sure enough, we see in this case that it's the end caps that have the flux going through it, but it's the sides that are parallel. So this is the key difference between the Gaussian cylinder versus that Gaussian pillbox. So let's apply what this would look like looking at the easy side of the equation. The easy side being the surface integral. Remember, I know it looks like a circle, but it's a sphere. And if we take this whole sphere, then we're going to take the surface area of it, which is 4 pi r squared. If you look at a Gaussian cylinder, it's going to be this loop right there, that circumference, multiplied by our length. And so this is going to be our E dot dA term for a Gaussian cylinder. For a Gaussian pillbox, you can do it either way, either as just the top end cap or the bottom end cap. And we're going to find out why this is the case in video 2. So let's look at an example. Here we have a bunch of charges, and I want to maximize the electric flux out of my Gaussian surface. So imagine what you'd have to do to draw it to make this happen. Here's our answer. You're like, wait, that's not a cylinder, you tricked me. Okay, sure, kind of indirectly, but the key idea is if we're doing quantitative, actually solving math, it's going to be one of those 3 Gaussian surfaces. However, Gauss's law always applies. It's just whether it's easy to solve. So for this one, this left side would be very difficult to work through with this particular weird shape, but we could actually use Gauss's law to help us get to an ultimate solution. It'd just be difficult. So we'd be more of a qualitative discussion. When we look at an enclosed charge, which is the one we have here, let's solve this particular problem where now this looks a little bit more straightforward. This is a conducting shell, so we have that spherical symmetry. I have a 4 and a negative 3. I want to know the charge that's enclosed to these different radii of r. Well, here, the only charge that's enclosed is the 4. So Q enclosed would just be 4 microcoulombs. If I go outside of it to this region here, I'm going to have +1. Why? Well, because it encloses all the positive 4 and the negative 3. So that's the total charge enclosed. And here might be a little tricky one. What about inside this conducting shell? Yes, it would just be 0. Why is it going to be 0? Because we know that the E field inside of a conductor is 0. So if this term right there has to be 0, our Q enclosed must be 0. As a fun little side point, to make this work, that means my inner surface would have to have a charge of -4 to cancel out that one. And my outer surface would have a charge of +1 to make it so the total charge on this outer surface, or at this outer shell, was still a -3 microcoulombs. So now let's look at this grounded conductor. We have the exact same setup, but now I've grounded this outer shell. And this time I want to know what the total charge on the surface of the inner and outer shells is going to be. Well, if I look at the inner shell, this has to be 0. Why does it have to end up being 0 E field enclosed? Because I'm inside of the conductor just like before. Well, if the inside is 4, and I'm trying to solve for what's on the inside surface of the shell, it's going to cancel out to make it so the inner surface has a charge of -4 microcoulombs on it. On the flip side, the outside surface is grounded. That means this whole system should become electrically neutral. So the outer surface is going to have 0 microcoulombs of charge on it. So here's a bonus question. What would the charge density be on this inner shell? Remember, this is a sphere. Well, charge density is just charge over area. The surface area of that inner surface is 4 pi a squared, because that's my radius. And if I plug things in, I would get that answer. This is kind of a typical way of looking at Gauss's law when it comes to the shapes and how do we solve for charge enclosed. Calculus is coming up in the future. So with this said, let's briefly talk about Maxwell's equations. And here's when I say briefly, this is what we're talking about. We just learned the first Maxwell's equation, which is Gauss's law for electrostatics. But you have 3 more in your wonderful journey throughout this course, and you get to look forward to those in topics 12 and 13. So when you get there, by the end, you'll know 4 different Maxwell's equations, which help dictate and govern all the different rules that govern electromagnetism. So look forward to that, but you've just started your journey on this first one. So what should we take away from this video? The main thing to take away is what Gauss's law is. So when somebody says use Gauss's law, this is the equation that we're using. Recognize how to use and when to use certain Gaussian surfaces. Recognize that the Gauss's law can help explain why conductors have 0 electric flux. And even though it's not listed here, there's the easy side and the hard side of Gauss's law to break down. And this last thing, that you have now started your quest, as it were, to discover all these different Maxwell's equations. So have fun, look forward to solving for the next 3. With that said, I look forward to seeing you in the next few videos where we actually apply Gauss's law to solve problems for different symmetries. See you then.